There is a secret buried inside everything you have ever seen, touched, loved, or feared. A secret so profound, so disorienting, that most people walk through their entire lives completely unaware of it. The ground beneath your feet, the air filling your lungs right now, the body carrying you through the world. None of it is what you think it is. None of it is what it appears to be. Strip away the surface of reality, peel back the layers of the visible world, and what you find underneath is something that should be impossible, something that defies every instinct your mind has developed over a lifetime of living inside a solid, tangible, dependable universe. What you find at the very foundation of everything is almost nothing at all. This is not a metaphor. This is not poetry. This is physics. And once you understand it, truly understand it, you will never look at the world the same way again. If this kind of journey through the hidden nature of reality fascinates you, it would mean so much to us if you liked this video and subscribed. It genuinely helps us keep exploring these ideas together. Every object around you right now, the walls, the floor, the device you are reading this on, your own hands, is constructed from invisible building blocks called atoms. You already know this. You learned it in school. Atoms make up matter. Matter makes up the world. Simple enough, comfortable enough. But what you were probably never told, what the neat diagrams and textbooks carefully avoided conveying, is what atoms actually are like on the inside. What they are truly made of, and how impossibly, devastatingly, almost offensively small they really are. Because the moment you begin to grasp the true scale of an atom, the actual, honest-to-physics size of the thing, something shifts. The world starts to look different, not frightening exactly, not dangerous, just deeply, wonderfully strange. Like a painting you have walked past every day for years, and one afternoon, the light catches it at a different angle, and you realize for the first time that everything you assumed you were seeing was wrong. Let us start with something reassuringly ordinary, a single strand of human hair. Hold it up if one is handy. Let it catch the light. It looks thin, doesn't it? Delicate, barely there. The width of a human hair is roughly 70 to 100 micrometers, about 1/10 of a millimeter, invisible at a glance, barely detectable between your fingertips. Most people think of a hair as the very definition of something thin and slight, and by the standards of everyday experience, it absolutely is. But a human hair is a skyscraper compared to an atom. Across the diameter of a single strand of hair, you could line up approximately 500,000 atoms side by side, 500,000 of them, shoulder to shoulder, and together they would span a distance your fingers can barely register. 500,000 of the fundamental building blocks of reality, packed into a gap so narrow it is practically invisible. Let that settle for a moment before we go any deeper, because we are just getting started. An atom measures roughly 1/10,000,000th of a meter across. Written out, that is 0.00000000001 meters. A decimal point, followed by 9 zeros and then a 1. The number is so telescopically small that the mind refuses to hold it. It slides away, like trying to grip water. So instead of working with raw numbers, let us do what the human imagination does best. Let us scale up. Let us build a bridge between the atomic world and the world you actually live in, one leap at a time. Imagine you are standing in a wide open field, holding a single blueberry, an ordinary blueberry, about 1 centimeter across. Small, round, unremarkable. Now ask yourself, if this blueberry were an atom, if we enlarged a real atom until it was the size of this blueberry, how big would the actual blueberry become in that same universe? How large would a blueberry appear if atoms were blueberry-sized? The answer is that the blueberry would be roughly the size of the Earth, the entire planet, all 12,700 kilometers of diameter, from the iron core to the highest mountain peak to the edge of the atmosphere. That is the ratio. That is the gap in scale between an atom and a blueberry. And now, consider that every single blueberry you have ever eaten contained more atoms than there are grains of sand on every beach and desert on the planet. Consider that the relationship between a blueberry and the Earth is the same as the relationship between one atom and that blueberry. Then multiply that blueberry by the trillions of atoms in your body, in the room, in the ocean outside, in the rock beneath the ocean floor. The universe is built from objects so small, they are effectively invisible not just to the naked eye, but to the very concept of visibility, since light itself, the thing we use to see, is too coarse, too bulky, too enormous to interact meaningfully with a single atom. Visible light travels in waves with lengths between roughly 400 and 700 nanometers. An atom is about 1/10 of a nanometer across. That means the light you use to see the world every waking moment of your life has wavelengths several thousand times larger than the atoms it is supposedly illuminating. Trying to see an atom with visible light is something like trying to feel the texture of a single grain of sand by pressing an ocean wave against it. The wave does not notice the grain. The grain does not disturb the wave. They exist in different scales of reality, and one simply passes through or around the other without interaction. This is why atoms were unknown for most of human history. Not hidden, not secret, just invisible in a way that goes deeper than ordinary invisibility. A tiger hiding in tall grass is invisible, but it is there, physical, detectable if you get close enough. An atom was invisible in a way that no amount of squinting, no sharpened lens, no ordinary proximity could overcome. It took centuries of inference, of reasoning from the behavior of matter in bulk, the way gases expand, the way chemicals react, the way electricity flows, before anyone could say with confidence that atoms were real and not just a convenient fiction. The ancient Greek thinker Democritus, working around 400 BCE in a world without microscopes or spectrometers or any of the instruments we now take for granted, proposed through pure philosophical reasoning that matter must be made of indivisible units. He called them atomos, meaning uncuttable. The logic was elegant. If you keep dividing a piece of stone in half over and over, you must eventually reach a piece so small that division becomes impossible. Otherwise, matter would be infinitely divisible, and an infinite number of physical pieces would fit inside a finite object, which struck him as absurd. So there had to be a smallest unit, a final, irreducible fragment of the material world. For over 2,000 years, this remained a philosophical position rather than a scientific one. The great Aristotle rejected it entirely. He believed matter was continuous, a single unbroken fabric of existence that could be divided forever without reaching any fundamental grain. Aristotle's authority was so colossal, his influence so deeply woven into the intellectual fabric of the ancient and medieval world, that his rejection of atoms essentially froze the idea for nearly 2 millennia. Democritus had the right instinct, but without evidence, an instinct is just a guess. Then, in the early 19th century, an English school teacher and amateur scientist named John Dalton began working through the mathematics of chemical reactions. He noticed something persistent and puzzling. Elements always combine with each other in fixed whole number ratios by weight. Hydrogen and oxygen always combine to form water, in a ratio of 1:8. Carbon and oxygen always combine in fixed proportions to form carbon dioxide. These ratios were stubborn, reproducible, universal. They did not care what temperature you ran the reaction at, or how much material you started with. The ratio held. Dalton realized that the only sensible explanation for this behavior was that each element was made of identical, indivisible particles, atoms, with specific weights, and that chemical reactions were simply the rearrangement of these particles into new combinations. The whole number ratios appeared because atoms were discrete. You could have one atom of hydrogen bonding with one atom of oxygen, or 2 atoms bonding with one, but you could not have 1.5 atoms bonding with one. Atoms were countable units, and their counting was what produced the beautiful, frustratingly consistent ratios he kept measuring in his laboratory. Dalton could not see atoms. Nobody could. But he could hear their mathematical fingerprints in the data, and that was enough to build a scientific case. Over the following decades, evidence accumulated from every corner of chemistry and physics. The behavior of gases could be explained beautifully if you imagine them as vast swarms of tiny particles bouncing around at high speed. The way electricity moved through solutions made sense if charged atoms were carrying the current. The colors of light emitted by heated elements, those sharp, precise spectral lines that appeared at specific wavelengths and nowhere else, whispered that something discrete was happening inside matter, something quantized and particular rather than smooth and continuous. By the late 19th century, the atomic theory was gaining real momentum, and then came the electron. In 1897, the British physicist J.J. Thomson was experimenting with cathode rays, beams of something that traveled through near vacuum tubes when a high voltage was applied. He bent these rays with magnetic and electric fields. He measured the way they deflected. And from those measurements, he deduced something extraordinary. The beams were made of particles much smaller than any atom, all identical regardless of what material the electrodes were made from. These particles, electrons, seemed to be universal. Every material, every element, every substance produced the same particles when pushed hard enough. This meant electrons were components of atoms themselves. For the first time, the atom had an interior. For the first time, the atom was not the smallest thing. Thomson's image of the atom was intuitive and, as it turned out, completely wrong. He imagined the atom as a kind of pudding, a diffuse sphere of positive electrical charge, with electrons embedded inside it like raisins dotted through a Christmas pudding. The positive and negative charges were spread evenly, mixed together, filling the atomic volume. The atom was, in this picture, a solid little ball of matter. Small, yes, but densely packed with substance. This made instinctive sense. Matter feels solid. Atoms should be solid. Everything about everyday experience pointed toward matter being continuous and filled in, right down to the smallest scale. Then Ernest Rutherford blew the model apart. In 1909, Rutherford was directing his colleagues Hans Geiger and Ernest Marsden in a now famous experiment at the University of Manchester. They were firing alpha particles, helium nuclei, small and fast and positively charged, at an extremely thin sheet of gold foil, only a few hundred atoms thick. Behind the foil, they placed a detector to catch the particles after they passed through. The experiment was designed to probe the internal structure of gold atoms to see if the positive charge inside them would deflect the incoming particles, and if so, by how much. Based on Thomson's pudding model, the predictions were clear and boring. The positive charge in the gold atoms was diffuse, spread thin across the whole atomic volume. The incoming alpha particles would encounter only a gentle, distributed electrical repulsion. They might be nudged slightly off course, like a stream of cannonballs passing through a fog, barely disturbed, mostly continuing in their original direction. A few degrees of deflection maybe, nothing dramatic. Rutherford expected the experiment to be a routine confirmation of the existing model, a box-ticking exercise before moving on to more interesting questions. Instead, something impossible happened. Most of the alpha particles behaved exactly as predicted. They sailed through the gold foil almost without deflection, as though the foil were not there at all, but a small fraction, a few particles in every 1,000, were deflected at enormous angles. Some bounced back at 90 degrees. A handful came almost directly back toward the source. Rutherford stared at the data and later described his reaction in words that have echoed through physics ever since. He said it was as if you had fired artillery shells at a sheet of tissue paper and found that some of them bounced back and hit you in the face. The only possible explanation was that the positive charge inside a gold atom was not spread evenly throughout its volume. It was concentrated in an almost incomprehensibly tiny region at the atom's center. When an alpha particle happened to pass near this tiny dense kernel of positive charge, the electromagnetic repulsion between the two was violent and intense, capable of flipping the particle's direction entirely. But this central region was so small, so astronomically, absurdly, almost impossibly small, that most alpha particles never came anywhere near it. They flew through the vast empty space of the atom's interior without encountering anything at all, passing through the gold foil the way a bullet passes through a room full of widely scattered marbles, mostly open air, occasionally a direct hit. The atom was not a solid pudding. It was almost entirely empty space, with a tiny, dense, positively charged nucleus sitting at its center. Rutherford published his analysis in 1911 and proposed the nuclear model of the atom, a minuscule nucleus containing virtually all the atom's mass, surrounded by electrons occupying the outer regions of the atom's volume, with the vast majority of that volume being nothing. Absolutely nothing. How empty is empty? The numbers require several attempts to land properly. The nucleus of a typical atom is roughly 100,000 times smaller in diameter than the atom itself, 100,000 times. When you take that ratio and apply it to volume, which scales with the cube of the diameter, the nucleus occupies approximately 1/4,000,000th of the atom's total volume, 1 divided by 1,000 trillion. That is the fraction of the atom that contains actual matter. Imagine a cathedral, one of the grandest ever built, Notre Dame de Paris, the Hagia Sophia, the interior of St. Peter's Basilica, with its soaring dome and its vast nave stretching away into shadows. Now, imagine that this entire cathedral, every cubic centimeter of space from floor to ceiling and wall to wall, represents a single atom. Now, ask where the nucleus is. It would be a grain of sand, a single grain of sand, perhaps barely visible on the floor beneath the Great Dome. That grain contains almost all the mass of everything represented by the cathedral. All the rest, the soaring arches, the stained light, the echoing emptiness between pillars, is void. Or try this. Imagine you expanded a hydrogen atom, the simplest, smallest atom with just one proton in its nucleus, until that nucleus was the size of a basketball. A regulation basketball, roughly 24 centimeters across. How large would the atom itself be, scaled by the same factor? The boundary of the atom, defined by where the single electron is most likely to be found, would lie roughly 12 kilometers away from the basketball. 12 kilometers, 7.5 miles, in every direction. The basketball sits at the center of a sphere 12 kilometers in radius, and between the basketball and the edge of that sphere, there is nothing. No walls, no scaffolding, no hidden structure, just space. You could start walking from the basketball and walk for miles in any direction through absolute featureless emptiness. And only as you approach the very edge of that 12-kilometer sphere would you encounter anything at all. A single electron, itself far smaller than the basketball, hovering somewhere in that outer region. The atom is almost entirely a vast, silent void with a speck of matter at its heart. This is what you are made of, not the solid, densely packed material your senses insist upon. A collection of mostly nothing, of gaps and voids and quantum whispers, held together in the shape of a human being by forces we will get to in a moment. 7 octillion atoms in the average human body, each one overwhelmingly empty. The nuclei of all those atoms, if you extracted them and packed them together with no gaps between them, would fit inside a cube smaller than a grain of fine beach sand, less than 1/10 of a millimeter on each side. That tiny speck would contain your entire mass, every kilogram of you, compressed into a volume your naked eye could barely detect. The rest of you, every cell, every bone, every stretch of skin, everything that makes you recognizable as a physical object occupying space in the world, is the electromagnetic architecture of empty atoms, a force-maintained illusion of solidity sculpted from nearly nothing. And if you removed the empty space from every human being alive on Earth today, all 8 billion of us, the remaining nuclear matter would fit inside something roughly the size of a sugar cube. 8 billion people, the entire current population of the planet. Their combined mass of nuclear material, dense as a neutron star, packed into a space you could hold between 2 fingers. A very heavy sugar cube. It would weigh several 100 billion kilograms, roughly the mass of a small asteroid. But physically, geometrically, it would be almost nothing at all. Now comes the part that cracks the mind open a little wider. The nucleus at the center of the atom contains protons and neutrons bound together with ferocious force. But the electrons surrounding it, the particles that define the atom's size, the particles that occupy, in probabilistic terms, that vast empty volume around the nucleus, those electrons are even more philosophically disturbing than the atom's emptiness. Because electrons do not behave like ordinary matter. They do not behave like planets in orbit, which is the picture most people carry from their school years. They do not trace paths. They do not travel in circles or ellipses. They do not have positions at all, in any conventional sense, until the moment they are measured. The story of how physicists discovered this, how they were dragged, sometimes screaming, from a comfortable classical picture into the strange luminous wilderness of quantum mechanics, is one of the great intellectual adventures in human history. It begins with a problem so simple that it sounds almost trivial, and ends with a view of reality so strange that one of the greatest physicists of the 20th century spent the last 3 decades of his life trying to argue against it. The problem was this: if electrons orbit the atomic nucleus the way planets orbit the sun, they should not exist. According to the well-established physics of electromagnetism, any charged particle moving in a curved path continuously radiates energy, This is not a theoretical prediction that requires subtle experiments to confirm. It is a robust, well-tested feature of classical physics. The reason radio antennas work is that accelerating electrons in metal rods radiate electromagnetic energy outward. The reason particle accelerators glow with X-rays is that the electrons being steered around their circular paths are radiating as they curve. Acceleration produces radiation, and an electron moving in a circular orbit is constantly accelerating because it is constantly changing direction. A classical orbiting electron should therefore shed energy continuously, spiraling inward toward the nucleus in a death spiral lasting about 16 trillionths of a second. The atom should collapse, almost instantaneously with a tiny flash of radiation as the electron falls into the nucleus. Every atom in the universe should disintegrate within a fraction of a nanosecond of forming. There should be no stable matter, no stars, no planets, no chemistry, no life. The universe should be a brief, hot spray of collapsing atoms followed by darkness. Instead, hydrogen atoms formed in the first minutes after the Big Bang more than 13 billion years ago are still with us today, completely unchanged. The atoms in a glass of water on your desk have been passing from one form to another, one creature to another, through geological and biological cycles for billions of years without once falling apart from the inside. Atoms are among the most stable structures in the known universe. Something was badly wrong with the classical picture. And in 1913, the young Danish physicist Niels Bohr made a bold, strange, half-justified patch. He proposed that electrons were only allowed to orbit at certain specific distances from the nucleus, and that, while in these special orbits, they would not radiate. Why? There was no good reason within classical physics. Bohr imposed the rule because the alternative was impossible, and because the rule worked. It worked remarkably well. Bohr's model correctly predicted the precise wavelengths of light emitted by hydrogen gas when it was excited by electricity. These so-called spectral lines had been measured with extraordinary accuracy for decades, and their pattern was deeply mysterious. Each element emitted a unique fingerprint of light, specific colors at specific wavelengths, as recognizable as a signature. Bohr's quantized orbit model reproduced hydrogen's fingerprint almost perfectly. For the first time, theory and spectroscopic observation agreed, but Bohr's model was, at its core, a patch on a broken framework. It told you where electrons were allowed to be, but not why. It worked beautifully for hydrogen and fell apart for anything more complex. It was still imagining the electron as a tiny ball, a miniature planet, following a defined circular path. It had forbidden the electron from falling inward by royal decree, without explaining the mechanism of the prohibition. The real revolution came in the 1920s, from several directions at once, in a burst of brilliance that reshaped physics more thoroughly than any period since Newton. And it began with a deeply strange idea proposed by a French aristocrat and doctoral student named Louis de Broglie. De Broglie's insight was this: if light, traditionally thought of as waves, could sometimes behave as particles, the photoelectric effect had demonstrated this convincingly, then perhaps particles like electrons could sometimes behave as waves, not metaphorically, not approximately. Actually, physically behave as waves, with genuine wavelengths and frequencies and interference patterns. This was a wild claim in 1924, but de Broglie backed it up with mathematics. He showed that the wavelength of a matter wave associated with a particle was inversely proportional to the particle's momentum. Heavy, fast objects have wavelengths so fantastically small they are undetectable, but light, slow objects, like electrons, have wavelengths comparable to atomic scales. And if electrons are waves, Bohr's mysterious allowed orbits suddenly make sense. Only orbits whose circumference contains a whole number of electron wavelengths are stable, because only in those orbits does the wave close smoothly upon itself instead of canceling its own interference. The orbits that Bohr had selected by fiat emerged naturally from wave behavior. De Broglie's idea was experimentally confirmed within a few years. Electrons passing through a crystalline material, a material with regularly spaced atomic layers acting like a diffraction grating, produced interference patterns identical to those produced by X-rays. Electrons were genuinely behaving as waves. Particles were waves. The boundary between the two, once thought absolute, dissolved. And then Erwin Schrödinger wrote down the equation. In 1926, working in isolation over a winter holiday, Schrödinger produced a mathematical description of how matter waves evolve in time and space. His wave equation, applied to the electron in a hydrogen atom, produced solutions, specific allowed wave patterns, that perfectly reproduce the spectral lines of hydrogen, the ones Bohr had struggled to explain with his arbitrary orbiting shells. But Schrödinger's solutions were not orbits. They were three-dimensional standing waves, complex shapes filling the space around the nucleus, each one corresponding to a different energy level. These shapes are called orbitals, and they are nothing like orbits. The simplest one, the ground state of hydrogen, the state the electron occupies when the atom is as low energy as it can be, is a sphere, not a ring, not a circle, not a path of any kind. A sphere of probability, densest at the nucleus and fading gradually with distance, like the glow around a lamp growing dimmer as you walk away from it. If you asked where the electron was at any given moment, the most honest answer would be probably somewhere in this sphere, with the probability of finding it at any specific point given by the wave function at that point. Probably, not certainly, probably. This is the moment where quantum mechanics parts company with everything that went before it. The wave function does not tell you where the electron is. It tells you where the electron might be found if you looked. Before you look, before any measurement is made, the electron does not have a position. It is spread across the probability cloud simultaneously in a superposition of all possible locations, weighted by their probability amplitudes. Only when a measurement forces the issue does the electron commit to a specific location. The act of measurement collapses the wave function, selecting one outcome from the range of possibilities and discarding the rest. This is deeply, profoundly different from ordinary uncertainty. When you say you are not sure whether your keys are on the kitchen table or in your coat pocket, what you mean is that the keys are definitely in one of those places, and you simply do not know which. The uncertainty is in your knowledge, not in the world. The keys exist somewhere. They have a location. You just do not know it. Quantum mechanics says something categorically different. Before measurement, the electron is not in a definite location that you happen to be ignorant of. It genuinely does not have a location. There is no fact of the matter about where it is. The question, where is the electron right now, has no answer. Not because the answer is hidden from you, but because there is no answer to be hidden. The electron's position before measurement is not unknown. It is undefined. The universe itself has not decided where the electron is. That decision is only made when a measurement forces the issue. Werner Heisenberg formalized this in 1927 with his uncertainty principle. The principle states that certain pairs of physical properties, most famously position and momentum, cannot simultaneously have precise values. The more precisely you pin down where a particle is, the more completely undefined its momentum becomes, and vice versa. This is not a statement about the limitations of measuring instruments. It is not because your equipment shakes or your detector is imprecise. It is a fundamental feature of reality at the quantum level. Precision in one of these paired properties generates irreducible uncertainty in the other. Nature enforces this limit absolutely, with no exceptions and no workarounds. Think about what this means for the concept of an electron orbit. An orbit requires you to know both the particle's position and its momentum at every instant, where it is and where it is going. Without both pieces of information, you cannot trace a trajectory. And Heisenberg's principle says, you can never have both pieces of information simultaneously. So, an orbit, in any conventional sense, is impossible. The electron does not have an orbit. The electron does not have a trajectory. The very conceptual framework that makes orbits possible, the idea of a particle moving along a defined path through space, does not apply at the quantum scale. The planetary model of the atom is not approximately right. It is categorically, architecturally wrong. It uses concepts that simply do not translate into the world it claims to describe. What replaces the orbit is the orbital, those complex three-dimensional probability distributions that Schrödinger's equation produces. Beyond the spherical ground state, the solutions grow progressively stranger and more beautiful. Some are shaped like dumbbells, two lobes of high probability pointing in opposite directions through the nucleus, with a node, a surface of zero probability, passing through the nucleus itself. The electron in this orbital is most likely to be found in one of the two lobes on either side of the nucleus, but is never found at the nucleus itself. It haunts the periphery while the center remains forbidden. At higher energies, the shapes multiply and elaborate. Four-lobed clovers, dumbbell shapes with rings around their middles, intricate geometric architectures of probability filling space in every direction. Each of these shapes is a precise mathematical solution to Schrödinger's equation. They are not invented or approximated or designed. They emerge from the mathematics as inevitably as the solution to an algebra problem emerges from the rules of arithmetic. The universe's wave equation has these shapes hardwired into it, and it imposes them on every atom in existence. These orbital shapes are the reason chemistry works, the reason carbon bonds to 4 other atoms and hydrogen bonds to 1. The reason DNA has the double helix structure that allows it to store and copy information. The reason water is a bent molecule with a permanent electrical asymmetry that makes it such an extraordinary solvent and so essential to life. Every chemical property of every element flows directly from the geometry of its electron orbitals, which flow directly from quantum mechanics, which is simply the actual, verified, rigorously tested description of how matter behaves at the smallest accessible scales. Albert Einstein famously could not accept this picture. He accepted the mathematics. He never disputed the predictions. Quantum mechanics made the most accurate quantitative predictions in the history of science, and Einstein knew it. What he could not accept was the implication that the world was fundamentally probabilistic at the quantum level, that God, as he put it, played dice. He spent years devising thought experiments intended to show that quantum mechanics must be incomplete, that there had to be hidden variables determining outcomes that looked random to us only because we lacked access to them. Electrons must have definite positions, he argued. They must have definite momenta. The uncertainty must be in our knowledge, not in the world itself. Niels Bohr, his great intellectual opponent on these questions, held firm. The universe was not hiding information from us. The universe genuinely was probabilistic at the quantum level. The experiment was the thing. And experiment after experiment, over decades, confirmed Bohr's interpretation. The decisive blow came from a theoretical insight by physicist John Bell in 1964. Bell proved mathematically that if particles had definite hidden properties determining their behavior, the kind of pre-existing reality Einstein required, then measurements on pairs of entangled particles would obey certain statistical limits. These limits became known as Bell's inequalities, and if quantum mechanics was correct, if particles genuinely lacked definite properties before measurement, those statistical limits would be violated. The experiments that followed, culminating in work by Alain Aspect in the 1980s, and refined by multiple teams over the following decades, consistently found violations of Bell's inequalities. The results agreed precisely with quantum mechanics and ruled out any hidden variable theory of the kind Einstein had hoped for. The 2022 Nobel Prize in Physics was awarded specifically for this body of experimental work. The universe is genuinely random at the quantum level. There are no hidden dice. The dice are the thing. The probability is not a gap in knowledge. It is the fabric of reality. And yet, and here is one of the deepest beauties of the story, this fundamentally probabilistic, uncertain, fuzzy quantum reality produces the solid, reliable, deterministic feeling world you navigate every day. Somehow, out of billions of atoms each governed by wave functions and probability clouds and irreducible uncertainty, emerges a world where coffee stays in cups, where bridges hold weight, where the sun rises at predictable times and bodies fall at predictable rates. How? Part of the answer is scale. When you average the behavior of enormous numbers of quantum uncertain particles, the statistical fluctuations wash out and smooth patterns dominate. A single atom behaves like a quantum object. Its electron has no definite position. Its energy levels are sharply quantized. Its behavior is ruled by probability. A mole of atoms, 600 billion trillion of them, behaves like a classical object, because the quantum weirdness of each individual atom is lost in the statistical roar of the crowd. The classical world you inhabit is the statistical residue of an unimaginably vast number of quantum events averaging themselves into the appearance of certainty. But scale alone does not explain why matter feels solid. For that, you need a different piece of the story. Because here's the thing. If atoms are mostly empty space, and if the matter inside atoms occupies less than 1/1,000,000th of the atomic volume, then why don't things pass through each other? Why doesn't your hand sink through the table? Why doesn't the floor absorb you? Why does anything stop anything else? When Rutherford's team fired alpha particles at gold foil, most of them sailed straight through as if the foil were not there. The foil was made of atoms. The atoms were mostly empty. The particles went right through the emptiness without encountering the nuclei, which were too small and too scattered to intercept most of them. The foil was, from the particles' perspective, almost a vacuum. So why can't you do the same thing with your hand? Why is the table an effective barrier when it is made of the same mostly empty atoms as the gold foil? The answer lies in electrons. When two atoms approach each other closely enough, their electron clouds, those fuzzy probabilistic spheres defining the atom's outer regions, begin to overlap. And when electron clouds overlap, a pair of powerful effects kick in simultaneously. The first is electromagnetic repulsion. Electrons carry negative electrical charge. Like charges repel each other. As two electron clouds push into each other's territory, the negatively charged electrons in each cloud push back against the negatively charged electrons in the other. This repulsive force grows rapidly as the overlap increases. It is not gradual or gentle. It escalates sharply, becoming more intense the closer the two clouds are pressed together. The closer you push two atoms, the harder their electron clouds resist. There is no gentle intermediate zone of mild resistance. The force is soft at long range and savage at short range, and it switches from one to the other over scales measured in angstroms, fractions of a nanometer. This electromagnetic repulsion is the force you feel when you press your hand against a table. Your atoms are not touching the table's atoms. The electron clouds of your atoms are being repelled by the electron clouds of the table's atoms, this with a force strong enough to stop your hand and hold it there, suspended by the electromagnetic interaction between clouds of probability-smeared electrons separated by a gap measured in fractions of a nanometer. At no point do your atoms make contact with the table's atoms. Contact, in the physical sense of two solid objects pressing against each other, does not happen at the atomic scale. What happens instead is a force balance, gravity pulling you down, electromagnetic repulsion pushing back up. And you experience the resulting equilibrium as the sensation of a surface beneath you. In a very literal and precise sense, you have never touched anything in your life. Not a table, not a floor, not another person's hand. Every sensation of contact you have ever felt has been electromagnetic force acting across a gap. Your entire lifetime of physical interaction with the world, every handshake, every step taken, every object picked up and held and set down, has been mediated by forces, not by matter meeting matter. You have been exquisitely invisibly insulated from direct physical contact with anything by electron clouds hovering at nanoscale distances from each other, doing all the physical work your senses experience as touch. But electromagnetic repulsion, powerful as it is, does not by itself fully explain the extraordinary impenetrability of matter. To understand that completely, you need one more piece, a rule so fundamental, so absolute, and so strange that it stands among the most important principles in all of physics. It is called the Pauli exclusion principle, and it was formulated in 1925 by the Austrian physicist Wolfgang Pauli. The principle states that no two identical fermions, electrons are fermions, as are protons and neutrons, can occupy the same quantum state simultaneously. A quantum state is a complete description of a particle in terms of all its quantum numbers, its energy level, its angular momentum, its spin orientation, its specific wave function configuration. Each unique combination of these properties constitutes a distinct quantum state, and each quantum state can be occupied by, at most, one electron at a time. This sounds like a rule about numbers and categories. In practice, it is a rule about space. When two atoms are pressed together and their electron clouds begin to overlap significantly, the electrons from one atom start invading the quantum territory of the other. But all the lower energy states in the second atom are already occupied by that atom's own electrons. The new electrons have nowhere to go in the energy landscape. They cannot drop into an occupied state. the exclusion principle absolutely prohibits it, so they are forced to jump to higher, unfilled energy states, and jumping to higher energy states costs energy. This energy cost manifests as a force, a repulsive force that resists compression, that pushes back against any attempt to squeeze atoms closer together than a certain minimum distance. This force, often called Pauli repulsion or degeneracy pressure, is what gives solid matter its ultimate hardness. It is not electromagnetic, it is purely quantum mechanical, a consequence of the impossibility of two identical fermions sharing a quantum state. And it is essentially impossible to overcome by any ordinary means. It is not a force that gets stronger and then eventually gives way under enough pressure. It is an absolute quantum mechanical prohibition, and overcoming it requires extreme conditions that exist nowhere in ordinary experience. The combination of electromagnetic repulsion and Pauli exclusion creates a barrier so effective that matter, despite being overwhelmingly empty space, behaves for all practical human purposes as though it were solid. Your body and the floor are both almost entirely nothing, but the forces operating between their electron clouds are so strong, acting across so many atom pairs simultaneously, that you are supported as reliably as though the floor were a single continuous slab of the densest imaginable material. Pauli exclusion also explains the structure of the periodic table. Electrons in an atom fill up the available quantum states starting from the lowest energy, just as water fills a vessel from the bottom. The first available shell can hold 2 electrons, the second can hold 8, the third can hold 18. These numbers are not arbitrary. They reflect exactly how many distinct quantum states are available at each energy level, how many unique combinations of energy, angular momentum, and spin are permitted by quantum mechanics at that level. Once a shell is full, the next electron has to go to the next higher shell. This sequential filling of quantum states is what gives each element its characteristic number of outer electrons, and it is those outer electrons, the ones in the partially filled outermost shell, that determine almost everything about an element's chemistry. How readily it reacts, with what other elements, in what proportions, with what energy released or absorbed. The entire edifice of chemistry is written in the filling order of electron shells, which is itself written in the language of the Pauli exclusion principle. Without this principle, all electrons would collapse into the lowest energy state. Every atom of every element would have the same electron configuration, the same chemical behavior, the same size. Hydrogen and gold and carbon and oxygen would all look the same to each other chemically. There would be no periodic table. There would be no organic chemistry, no biological molecules, no proteins, no DNA, no evolution, no life. The staggering diversity of matter in the universe, every compound, every mineral, every polymer, every living cell, depends on the Pauli exclusion principle forcing electrons into different states and thereby giving atoms different personalities, different affinities, different abilities to combine. Consider for a moment what it means that the hardness of a diamond, one of the hardest natural materials on Earth, is a quantum mechanical effect. Carbon atoms in diamond are arranged in a rigid three-dimensional lattice, each carbon atom bonded to 4 others in a tetrahedral geometry. This geometry arises from the shapes of carbon's electron orbitals and the quantum mechanical rules governing how orbitals from neighboring atoms can combine into shared bonding states. The incredible resistance to deformation that makes diamonds so hard is a manifestation of the enormous energy required to distort these quantum mechanically determined bonding arrangements. Hardness is quantum mechanics made tactile. Consider that the color of the sky is also a quantum mechanical effect, mediated by how light interacts with the electron structures of nitrogen and oxygen molecules, or that the chemistry of combustion, fire, is electrons rearranging themselves among molecular orbitals, releasing energy as they fall into lower states, or that the rust slowly claiming an iron railing in the rain is oxygen atoms peeling electrons from iron atoms through quantum mechanical bonding. Every chemical reaction in the universe, every transformation of matter, every interaction between molecules, every metabolic process in every living cell on Earth is electron behavior. Quantum mechanics is not a theory about abstract particles in a laboratory. It is the operational manual for every material process in the universe, and your body is running this manual right now at a scale that staggers comprehension. The roughly 7 octillion atoms in your body are each conducting their quantum mechanical affairs simultaneously, every electron in every orbital following the rules of the wave equation, every chemical bond maintained by shared electron states, every neural signal you carry propagating through cascades of ion channel openings and closings that are fundamentally quantum in nature. When you form a memory, the strength of a synapse is adjusted by the physical movement of protein molecules across cellular membranes, movements driven by chemical reactions, which are electron rearrangements, which are quantum processes. Your memories are quantum mechanics. Your thoughts are quantum mechanics. The process by which you are right now reading and understanding these words is quantum mechanics. And none of the atoms doing all this work have ever touched each other. Every bond, every interaction, every force is conducted across the empty void between electron clouds. The body you inhabit is a standing wave of electromagnetic and quantum mechanical interactions, maintaining a complex organized structure in defiance of entropy, drawing energy from food and using it to keep the pattern alive. You are, at the most fundamental level, a persistent shape maintained in otherwise formless emptiness by rules written into the mathematics of the universe. There is one more place where this story becomes almost unbearably strange. One more place where the quantum emptiness of matter reveals itself in spectacular fashion, in objects so extreme that they stretch the imagination past any comfortable limit. When a massive star, many times heavier than our sun, exhausts its nuclear fuel and collapses, the gravitational force pulling its matter inward becomes so overwhelming that it overcomes the electromagnetic and Pauli exclusion forces that have maintained the star's structure for millions or billions of years. Those forces which support mountains and hold oceans in place and prevent your feet from falling through the ground are simply crushed. The electrons are driven into the atomic nuclei under such enormous pressure that they merge with the protons, producing neutrons. The entire stellar core collapses into a ball of pure neutrons, packed together at nuclear density, with no electron clouds, no empty atomic interiors, no void of any kind. Just neutrons touching neutrons, packed as tightly as quantum mechanics allows. The resulting object is a neutron star. A typical one is about 20 kilometers across, smaller than many cities, smaller than some mountain ranges. Yet it contains between 1 and 2 times the mass of the entire sun. Hundreds of thousands of Earth masses compressed into a sphere you could drive across in 20 minutes. A teaspoon of neutron star material would weigh approximately 6 billion tons on Earth's surface. This is matter with all the empty space removed, compressed to the density of an atomic nucleus, existing as a city-sized ball of raw nuclear material spinning hundreds of times per second, generating magnetic fields 1 trillion times stronger than Earth's. This is what happens when the forces that create the illusion of solidity in ordinary matter are finally overcome. The atom's emptiness is forcibly eliminated, and what remains is neutrons packed at unimaginable density, held in that state not by chemistry or electron orbitals, but by gravity so extreme that the escape velocity at the neutron star's surface approaches a significant fraction of the speed of light. Go slightly more extreme, push slightly more mass into slightly less space, and even that fails, and the collapse continues without limit into a black hole, where space and time themselves bend around the concentrated mass until the ordinary concepts of inside and outside cease to apply. The empty atom, the mostly nothing building block of reality, contains within it the seeds of the universe's most extreme objects. The emptiness is not weakness, it is structure. It is the canvas on which forces paint everything that exists. Now take a breath, an ordinary, unremarkable breath of air. The air flowing into your lungs right now contains about 25 billion molecules per cubic centimeter. In a single breath, you might inhale something on the order of several cubic liters of air, a volume containing numbers of molecules that make even the number of stars in the observable universe look modest. Each molecule is nitrogen or oxygen or argon or carbon dioxide, made of 2 or 3 atoms bonded by shared electron states. Each atom contains its vast interior emptiness, its tiny nucleus, its probability cloud electrons. Each electron has no definite position until some interaction forces one. All of these molecules are moving at speeds averaging around 500 meters per second, faster than a bullet, faster than the speed of sound, crashing into each other hundreds of billions of times per second and crashing into the interior surfaces of your lungs, and crashing into the molecules of your blood, and driving the oxygen chemically into the hemoglobin proteins in your red blood cells in a quantum mechanical bonding reaction that has been perfected by evolution over hundreds of millions of years. Every breath is a universe of quantum events. Every heartbeat moves a tide of mostly empty atoms through channels and vessels maintained by protein structures that are themselves quantum mechanical architectures of electron orbitals. The smell of rain, the taste of salt, the burning sensation of a pepper. All of these are molecular events, electrons and receptor proteins responding to the geometry of incoming molecules, sending electrochemical signals up nerve fibers to a brain that decodes them into sensation. Every sense you have is a quantum mechanical instrument. Every experience of the world filters through the atomic and subatomic fabric of matter. The solid world, the beautiful, dependable, tangible world, where tables stay on floors and walls contain rooms and people maintain their shapes from one day to the next, is an achievement, not a given, not a default. An achievement maintained moment to moment by the restless operation of forces across the empty interior of atoms, the quantum mechanical imperatives of electron exclusion, the electromagnetic bonds that tie atoms into molecules and molecules into the complex organized structures of living things. Look at your hand again, the same hand you have always had, the same hand that has always seemed so solid, so obviously, unambiguously physical. It contains roughly 27 trillion atoms just in a few cubic centimeters of tissue. Their nuclei, all the actual matter, all the genuine substance, would fit in a speck smaller than a bacterium if compressed together. Everything else, every visible, tangible cubic centimeter of your hand, is the organized emptiness of electron clouds and the forces they exert on each other. You are leaning on force fields when you place your hand on a surface. You are breathing storms of quantum mechanical particles when you inhale. You are seeing the world through photons that your eye's quantum receptors catch one by one, converting their energy into neural signals. You are the universe examining itself, matter contemplating the nature of matter, mostly nothing, wondering what it means to exist. And the wondering itself, that process of curiosity and reflection happening right now in the electrochemical landscape of your brain, is atoms. Neurons firing in patterns determined by synaptic strengths, shaped by decades of experience. Each synaptic signal is a cascade of ion channel proteins opening and closing, letting charged atoms flood through cell membranes and pulses of electrochemical activity. Each ion channel is a protein, a folded molecular machine held in its functional shape by quantum mechanical bonding between its constituent atoms. Your thoughts are, at the bottom, the behavior of electrons in orbital configurations, following the rules of a wave equation written into the fabric of the universe more than 13 billion years ago. The thought you are having right now, whatever it is, wonder or skepticism, or the quiet discomfort of a worldview being gently destabilized, is quantum mechanics. The universe, composed of mostly empty atoms governed by probability and wave functions and absolute quantum prohibitions, has arranged a portion of itself into a structure capable of understanding that it is composed of mostly empty atoms governed by probability and wave functions and absolute quantum prohibitions. There is no word in any language adequate to that. Wonder is close. Awe is close. Vertigo is also close, in a different way. The sensation of standing at the edge of something very deep and very real, and looking down into it. The atom is not what your textbook suggested. It is not a miniature solar system of particles orbiting a central mass along defined paths. It is a vast cathedral of emptiness with a speck of nuclear matter at its heart and a ghost of electron probability haunting its outer regions. Electrons that have no precise location, whose positions are not merely unknown, but genuinely undefined until the moment a measurement forces the universe to decide. The atom is built from rules rather than substance, forces rather than solidity, probability rather than certainty. And from these impossible, counterintuitive, quantized, probabilistic, wave mechanical building blocks. The universe has made everything. Every star in the sky, burning for billions of years on nuclear reactions between atomic nuclei. Every planet, layered and complex and geologically active over geological timescales. Every ocean and atmosphere and forest and creature that has ever existed on any of those planets. Every thought that has ever been thought. Every piece of music ever played. Every discovery ever made, including the discovery that atoms exist and what they are and how they work. All of it. From almost nothing at all. If you pressed your hand against the wall and felt it resist, felt it firm and unyielding and present, that resistance is not the universe confirming that matter is solid. It is the universe demonstrating, 1 trillion electron interactions at a time, how forces operating across emptiness can feel indistinguishable from something substantial. It is, in a sense, the universe being more creative than solid matter would require. It does not need solidity. It achieves the same result, the same stable, navigable, touchable, beautiful physical reality, from components that are basically nothing using rules rather than stuff, and that, perhaps more than any single fact about atomic size or nuclear density or quantum probability, is the most profound thing to take from this journey into the heart of matter. The universe chose not to build with solid bricks. It built with rules and forces and the strange, beautiful mathematics of quantum mechanics. And from those tools, it assembled a world so convincing that its inhabitants spend most of their lives unaware that the solid ground beneath them is a fiction maintained by forces they cannot see, stretched across voids they cannot feel, built from building blocks they cannot touch, following laws they cannot directly observe. The world is not solid. It is something better than solid. It is organized emptiness, held in shape by forces, written in the language of quantum mechanics, vast and strange and intimate and immediate all at once. It is the universe dreaming itself into existence from the inside, using almost nothing to make everything and, in at least one remarkable corner of one unremarkable galaxy, producing creatures capable of noticing and wondering and being quietly astonished. You are one of those creatures, and the empty atoms inside you have been rearranging themselves, firing electrochemical signals, maintaining the improbable organized structure of your body and your mind for every moment of your existence. They have never once touched anything. They have never once ceased their quantum mechanical business. They have been doing all of this for all of your life, without your knowledge and without your permission, following rules laid down at the beginning of time. The universe is stranger and more generous than it needed to be. It is generous with its strangeness, and the strangest, most generous thing about it may simply be this: that it is here at all, and that you are here inside it, made of the same almost nothing as everything else, and capable of knowing it. That is what an atom is. That is what you are made of. That is what this is. But the story does not end there, because once you accept the reality of the quantum atom, once the picture settles in your mind of electron clouds and nuclear specks and force-mediated solidity, a new set of questions opens up, each one deeper and stranger than the last. Questions that physicists have spent a century wrestling with and have not entirely resolved. Questions about what is inside the nucleus itself, about what holds it together, and about why the forces that govern the atomic world feel so alien to everything we know at human scales. Let us go inward one more time, past the electron cloud, past the vast emptiness of the atom's interior, down to the nucleus itself. The nucleus, that tiny, incomprehensibly dense kernel at the heart of the atom, is itself a world of extraordinary complexity. It contains protons and neutrons, collectively called nucleons, packed together at densities that dwarf anything achievable in ordinary matter. A teaspoon of pure nuclear material, every proton and neutron packed together with no gaps between them, would weigh approximately 200 million tons. That is the density inside every nucleus in every atom in your body right now. Inside your bones, inside the cells of your skin, inside the neurons currently processing these words. There are countless nuclei, each containing matter at that incomprehensible density. But the nucleus presents a puzzle of its own. Protons carry positive electrical charge. Positive charges repel each other. The electromagnetic force between two protons separated by a femtometer, the scale of the nucleus, is enormous, on the order of tens of newtons acting on particles with masses of roughly 1.67 times 10 to the minus 27 kilograms. That is a staggering force acting on an almost incomprehensibly light object. Left to their own electromagnetic devices, protons inside a nucleus should explode outward from each other with extraordinary violence, like a compressed spring suddenly released. Every nucleus in existence should fly apart in an instant. They do not. The nuclei and the carbon atoms of your body have been intact for as long as those carbon atoms have existed, which in many cases means billions of years, forged in stellar interiors long before the solar system formed. Something holds them together. Something overpowers the electromagnetic repulsion between protons at nuclear distances and binds the nucleons into stable, coherent structures. That something is the strong nuclear force, arguably the most powerful force in nature over short distances, and almost certainly the least intuitive. Unlike the electromagnetic force, which operates over unlimited distances and decreases smoothly with the inverse square of separation, the strong force has a range of roughly 1 femtometer, about the diameter of a proton. Within that range, it is overpoweringly attractive, strong enough to overwhelm electromagnetic repulsion by a factor of approximately 100. Beyond that range, it effectively vanishes. An object more than a couple of femtometers from a nucleon feels essentially no strong force whatsoever. This combination of immense short-range attraction and zero long-range influence is what gives atomic nuclei their characteristic structure. Pack protons and neutrons close enough together within a femtometer of each other, and the strong force binds them with tremendous power. But that binding has limits. Add too many protons to a nucleus, and the electromagnetic repulsion between them, which acts between all pairs of protons regardless of distance, begins to overwhelm the strong force's short-range glue. Large nuclei become progressively less stable as the electromagnetic repulsion accumulates. Elements beyond iron on the periodic table require increasingly exotic combinations of protons and neutrons to maintain stability, and the heaviest naturally occurring elements, uranium, thorium, the actinides, are all inherently unstable to various degrees, slowly decaying over time scales ranging from billions of years to microseconds. This is radioactivity, the nucleus spontaneously reconfiguring itself to achieve a more stable arrangement, emitting particles and energy in the process. When uranium decays, the nucleus is not breaking down because something has gone wrong. It is optimizing, following the mathematics of nuclear binding energy toward a more favorable arrangement, shedding excess protons and neutrons in the form of alpha particles, or converting protons to neutrons via beta decay, each step releasing energy stored in the differences between nuclear binding states. The energy released by these nuclear rearrangements is the energy that powers nuclear reactors and nuclear weapons, and it is also the energy that has powered the sun for the past 4.5 billion years and will continue to power it for roughly another 5 billion more. The sun's luminosity, the 3,800 yottawatts of energy it pours into space every second, comes entirely from nuclear reactions in its core. Hydrogen nuclei, protons, are being fused together under the enormous pressures and temperatures of the solar interior, producing helium nuclei and releasing energy in the process. Each fusion event releases about 26 mega-electron volts of energy, equivalent to the energy needed to lift a grain of sand by a few centimeters. That sounds inconsequential, but the sun fuses roughly 600 million tons of hydrogen into helium every second. The aggregate of all those tiny nuclear events is the light that drives every ecosystem on Earth and has done so for most of the planet's existence. Every photon of sunlight that has ever struck your skin began as a nuclear event deep inside the sun, a pair of protons merging under conditions of temperature and pressure that would obliterate any ordinary matter in an instant. The energy released in that fusion traveled outward through the sun's interior, bouncing and scattering and being absorbed and re-emitted over a journey that took tens of thousands of years before finally reaching the surface and escaping into space. 8 minutes later, it struck you. The warmth you feel on a sunny day is the echo of nuclear reactions that began their outward journey before humanity's ancestors learned to use fire. The nucleons themselves, protons and neutrons, are not the end of the story. In the 1960s, experiments at particle accelerators showed that protons and neutrons were not elementary particles, but were themselves made of smaller constituents. High-energy electrons fired at protons revealed that the proton's mass was not distributed smoothly throughout its volume. There were hard little points inside, scattering centers that the electrons bounced off at large angles, just as Rutherford's alpha particles had once bounced off atomic nuclei. The proton had an interior structure. Those interior constituents are called quarks. Each proton contains 3 quarks, held together by a force carried by particles called gluons. The strong nuclear force, at its most fundamental level, is the interaction between quarks mediated by gluons. Quarks come in 6 varieties called flavors, with names that reflect the slightly whimsical mood of the physicists who discovered them: up, down, strange, charm, bottom, and top. Ordinary matter is made almost entirely of up quarks and down quarks. A proton contains 2 up quarks and 1 down quark. A neutron contains 1 up quark and 2 down quarks. Everything you see, everything you touch, every atom in the universe is ultimately built from combinations of these 2 quark types, plus the electrons surrounding atomic nuclei. The quarks inside a proton are confined there by a peculiarity of the strong force. Unlike most forces, the strong force between quarks does not weaken as they are pulled apart. Instead, it remains approximately constant, like a rubber band. The further you try to pull 2 quarks apart, the more energy you invest in the rubber band of the strong force between them. At a certain point, enough energy has been stored that it becomes more energical for the force to simply create a new quark-antiquark pair from pure energy. The energy in the field materializing as mass in accordance with Einstein's equivalence of mass and energy, rather than continue stretching. The result is not a pair of free quarks, but 2 new composite particles, each containing quarks. Free quarks have never been observed. The strong force does not permit them to travel unbound. This confinement is one of the deepest unsolved problems in theoretical physics. We know it happens. We can calculate its consequences with some precision. But a complete mathematical explanation of why quarks are confined, a derivation of confinement from first principles, remains elusive. The Clay Mathematics Institute lists it as one of 7 Millennium Prize problems in mathematics. Problems so deep and important that their solutions carry a $1 million prize. Confinement has not been solved. This is worth pausing on. The structure of the proton, the particle making up the nucleus of the simplest atom, hydrogen, the most abundant element in the universe, is not fully understood from first principles. We cannot derive the proton's properties rigorously from the fundamental equations of the theory governing quarks and gluons. We know the theory is correct because its predictions agree with experiment to extraordinary precision. But the mathematical tools to extract all the theory's consequences are, in some cases, not yet fully developed. The most abundant particle in ordinary matter contains a mathematical mystery at its heart, and the quarks are presumably not the end either. Whether quarks and electrons are themselves made of smaller constituents, or whether they are truly elementary, points of interaction in quantum fields with no internal structure, is a question that current experiments cannot answer. The energies required to probe the interior structure of a quark, if it has one, are far beyond the reach of any existing particle accelerator. The question is open. What we do know is this: at every scale we have probed, the universe reveals new layers of structure. The atom has a nucleus. The nucleus has protons and neutrons. Protons and neutrons have quarks. Quarks may or may not have further structure. Each layer is governed by forces that are stranger and more powerful and more tightly confined than the layer above it. Each layer is separated from the one above by staggering differences in scale. The quarks inside a proton occupy a space about 1,000th the diameter of the proton, which is itself 100,000th the diameter of the atom, which is already a 10 billionth of a meter. The rabbit hole goes down further with each generation of discovery. The universe appears to be structured in layers of organization, each one nested inside the one above, each one obeying rules that are invisible from the level above. You interact with the world at the level of macroscopic objects, things large enough to see and touch and feel. The objects you interact with are made of molecules. The molecules are made of atoms. The atoms are made of nuclei and electrons. The nuclei are made of protons and neutrons. The protons and neutrons are made of quarks. Below quarks, we do not know. At some level, presumably you hit bottom. At some scale, the subdivision ends. Whether that bottom is strings vibrating in a 10-dimensional mathematical space, as some theoretical frameworks suggest, or something else entirely, or whether the concept of a bottom even makes sense, remains one of the deepest open questions in physics. But from where we stand, the atom is the relevant level of organization for chemistry and biology and most of the processes that shape the world we inhabit. And the atom's architecture, its vast emptiness, its quantum mechanical electron cloud, its tiny dense nucleus, the forces holding it together and governing its behavior, is sufficient to explain almost everything about the material world at human scales. Consider water, the molecule that covers most of Earth's surface and constitutes most of your body. A water molecule is two hydrogen atoms bonded to one oxygen atom in a bent geometry, with the two hydrogens making an angle of about 104 degrees at the oxygen. This specific geometry, not a straight line, not a right angle, but precisely that particular angle, arises from the quantum mechanical arrangement of oxygen's electron orbitals. Oxygen has 6 electrons in its outer shell and wants 8 to fill it. It bonds with 2 hydrogens, each contributing 1 electron to a shared bonding orbital. The 2 lone pairs of electrons remaining on the oxygen push against the bonding pairs, compressing the angle between the 2 hydrogen-oxygen bonds to slightly less than the tetrahedral angle of 109 degrees. The precise molecular geometry is a direct consequence of quantum mechanical orbital shapes, and that geometry is the reason Earth has liquid oceans. The slight asymmetry of the water molecule, oxygen pulling electron density toward itself more strongly than the hydrogens, means that the oxygen end of the molecule carries a slight negative charge, and the hydrogen ends carry slight positive charges. This electrical polarity makes water molecules attract each other through what chemists call hydrogen bonds. The positive hydrogen end of one molecule is attracted to the negative oxygen end of another. These bonds are much weaker than the covalent bonds holding each water molecule together, but they are strong enough to keep water molecules loosely associated with each other, even at temperatures where many other molecules would have evaporated. The result is that water stays liquid at temperatures that are unusual for a molecule of its size. By comparison to other molecules of similar molecular weight, water has an abnormally high boiling point and an abnormally high heat capacity. It takes more energy to heat water than to heat most materials, which is why the oceans moderate Earth's climate so effectively, absorbing enormous amounts of thermal energy from the sun during summer and releasing it slowly during winter. The hydrogen bond network in water, which is itself a consequence of molecular geometry, which is itself a consequence of electron orbital shapes, which is itself a consequence of quantum mechanics, is directly responsible for the thermal stability of Earth's climate and the habitability of its surface. The same hydrogen bonding that stabilizes liquid water also maintains the double helix structure of DNA. The 2 strands of the helix are held together by hydrogen bonds between complementary base pairs, adenine bonding with thymine, guanine bonding with cytosine, across the center of the spiral. These bonds are weak enough that cellular machinery can separate the 2 strands to read or copy the genetic sequence, but strong enough to maintain the helix's integrity under ordinary cellular conditions. The information storage system at the heart of every living organism on Earth is stabilized by the same quantum mechanical interaction, the same consequence of electron orbital geometry that makes Earth's oceans possible. Carbon, the backbone of organic chemistry, and the element without which life, as we know it, is inconceivable, owes its extraordinary versatility to the shape of its electron orbitals. Carbon sits at the intersection of an unusual property. Its 4 outer shell electrons can hybridize their orbitals into 4 equivalent, symmetrically arranged bonding directions pointing toward the corners of a tetrahedron. This gives carbon the ability to form 4 strong bonds in 3-dimensional space, allowing it to serve as the branching point in elaborate molecular architectures. Long carbon chains can fold and twist. Carbon can form double bonds with itself or with other atoms, creating flat, rigid molecular segments. Carbon can form aromatic ring structures, the benzene ring and its relatives, that are flat, stable, and capable of stacking on each other like molecular pancakes, a property exploited by every organism that builds cell membranes. The diversity of organic chemistry, the millions of distinct carbon-based compounds that have been identified or synthesized, the tens of thousands of different molecular species operating inside a single living cell, all flows from the geometry of carbon's orbital hybridization, which flows from quantum mechanics, which operates according to rules established in the moments after the Big Bang. In those first seconds and minutes of cosmic history, the universe was a hot, dense plasma, too energetic for even atoms to form. Protons and neutrons existed as free particles, along with electrons and neutrinos and photons, all colliding in a primordial soup of radiation and matter. Within the first few minutes, as the universe expanded and cooled, the strong force began assembling some of those free protons and neutrons into helium nuclei, deuterium nuclei, and trace amounts of lithium. This was Big Bang nucleosynthesis, the forging of the first atomic nuclei, and it produced the initial cosmic inventory of elements, roughly 75% hydrogen and 25% helium, with tiny traces of lithium and essentially none of anything else. The universe at that point was a featureless, nearly uniform sea of atomic hydrogen and helium, cooling slowly, with density fluctuations of only 1 part in 100,000. From this almost perfectly smooth initial condition, gravity spent hundreds of millions of years pulling matter together, amplifying those tiny density fluctuations into knots and filaments and sheets, eventually collapsing the densest regions into the first stars. And the first stars, large, hot, burning brilliantly for only a few million years before exploding, did something essential. They fused the primordial hydrogen into heavier elements. The fusion of hydrogen into helium is the first step, then the fusion of helium into carbon, then carbon into oxygen. In the most massive stars, this ladder of fusion continues all the way up to iron. Each step releases energy, because each step produces nuclei with stronger binding forces per nucleon. Nuclei where the constituent protons and neutrons are more tightly and efficiently packed. Iron is the end of this ladder. Fusing iron does not release energy, it costs energy. The moment an iron core develops in a massive star, that star's days are numbered. Without energy production to support it, the core collapses under its own gravity in a fraction of a second, producing the explosive death of a supernova. The supernova explosion is so energetic, so extreme in its conditions of temperature and density, that it drives nucleosynthesis beyond iron, forcing atomic nuclei to capture neutrons faster than they can decay, building up the full range of heavy elements: nickel, copper, zinc, tin, iodine, gold, lead, uranium, in a rapid cascade of nuclear reactions that happens in seconds as the star dies. These heavy elements, ejected into space by the explosion, mix with the surrounding interstellar gas and dust. Over millions of years, that enriched material gravitationally collapses into new stars and planetary systems. The iron in your red blood cells, the calcium in your bones, the iodine your thyroid requires to function, the copper that helps your enzymes catalyze vital reactions. All of it was forged in stellar explosions that happened billions of years ago, before the solar system existed. You are made of stardust. This is not a metaphor. The heavy atoms in your body have a cosmic history. They were nuclear reactions in a dying star. They were ejecta in a supernova blast. They were interstellar gas clouds. They were planetary material. They were oceans and minerals and living organisms and oceans again, cycling through geological and biological processes for billions of years before becoming you. The carbon in your DNA was once in a stellar core, fused from helium in the triple alpha process that requires 3 helium nuclei to collide almost simultaneously, an event so improbable that the astrophysicist Fred Hoyle famously argued in the 1950s that the nuclear physics must include a resonance, a quantum mechanical enhancement of the reaction rate, at exactly the right energy to make the process proceed efficiently enough to account for the carbon abundance in the universe. The resonance, which Hoyle predicted before it was measured, exists. Its existence appears to be a consequence of the specific values of the fundamental physical constants of nature: the strength of the strong force, the electromagnetics force, the specific mass of the carbon nucleus. If any of these values were slightly different, the resonance would be in the wrong place and carbon would be rare in the universe. There would be no carbon-based chemistry. There would be no life. This is sometimes called fine-tuning, and it is a genuinely puzzling feature of the universe. The fundamental constants of nature appear to have values that permit the existence of complex chemistry and life. Whether this means anything, whether it reflects some underlying principle or some selection effect in a vast ensemble of universes with varying constants, or whether it is simply a remarkable coincidence, is one of the deepest and most genuinely unsettled questions in cosmology and fundamental physics. It does not have a consensus answer, but it points toward the remarkable contingency of the atomic world you inhabit, the fact that the specific properties of atoms, which flow from the specific values of fundamental constants, are precisely calibrated to permit a universe in which stars burn for billions of years. Carbon forms stable organic molecules, water maintains a liquid phase at biologically useful temperatures, and the periodic table contains enough variety to support complex chemistry. The universe did not have to be this way. It could have had different constants, different particles, different forces, a different atomic structure entirely. The fact that it has the structure it has, that atoms are the size they are, with the properties they have, governed by the rules they follow, is either profoundly meaningful or profoundly lucky. And physics currently cannot tell us which. What physics can tell us is how atoms behave when we observe them with our most sensitive instruments. And what we find is that even the act of observation is constrained by the quantum rules governing atomic behavior. When scientists first succeeded in producing images of individual atoms in the 1950s and 1960s with the field ion microscope and later with the scanning tunneling microscope developed in 1981, what they saw was not atoms as discrete hard spheres but as fuzzy blobs of electromagnetic influence. Atoms manifest as bumps in electrical current, mapped by an instrument so sensitive it could track the presence of a single electron tunneling across a gap measured in angstroms. The images that resulted, rows and clusters of soft, overlapping mounds, like eggs in a carton seen through fog, were the closest thing to a photograph of an atom that physics permits. Not a direct image produced by light, since light cannot interact with something so small in a way that preserves detail. A map of quantum mechanical interactions, translated into visual form by human ingenuity. In 1989, scientists at IBM used a scanning tunneling microscope not merely to see atoms, but to move them. They positioned 35 individual xenon atoms on a nickel surface, each atom placed with deliberate, controlled precision to spell out the 3 letters of their employer's name. The letters were 5 nanometers tall. The achievement was not primarily a demonstration of corporate loyalty. It was a proof of concept that the individual atoms which make up the material world are accessible to manipulation at the individual atom level, that the building blocks of reality can be picked up and placed by human hands if those hands are extended through the appropriate instrumentation. Since that demonstration, the manipulation of individual atoms has grown into an entire field of research and technology. Quantum computers, some of which are now commercially available, use individual atoms or individual electrons as the physical instantiation of qubits, quantum mechanical bits of information that can exist in superpositions of 0 and 1 simultaneously, leveraging quantum uncertainty to perform certain classes of calculations exponentially faster than any classical computer, the same quantum indeterminacy that Einstein struggled to accept, the same fundamental probability that made him argue that God surely could not be playing dice, is now being deliberately harnessed as a computational resource. Molecular machines, nanoscale mechanical devices assembled from atoms, have been constructed, studied, and even awarded the Nobel Prize in Chemistry in 2016 for the design and synthesis of molecular machines. These are not metaphorical machines. They are physical objects, made of atoms bonded in specific configurations, that perform mechanical functions, rotation, translation, contraction, in response to energy inputs. They are atoms arranged into devices by human design, following principles of chemistry that are principles of quantum mechanics. The atomic world is not merely something to be observed. It is becoming something to be engineered. At the far edge of this engineering program lies the possibility of building structures atom by atom, placing each atomic component in its intended position with sub-nanometer precision. This is still far beyond current practical capability for complex structures, but the conceptual framework is established and the incremental progress is real. The atoms that make up your world, those vast empty cathedrals of quantum probability, are becoming, slowly, materials to be worked with at their own scale. And yet, for all of this human ingenuity, for all the instruments and theories and Nobel Prizes accumulated in the centuries since Rutherford first demonstrated the atom's emptiness, the quantum world remains deeply alien. It remains a place where common sense is not just unhelpful, but actively misleading, where particles are also waves, and waves are also particles, where measuring something changes it, where two particles can be entangled across any distance such that measuring one instantly determines the outcome of measuring the other, regardless of how far apart they are. A phenomenon Einstein called spooky action at a distance and dismissed as impossible, but which has been experimentally confirmed so thoroughly that it now underlies practical quantum communication technologies. Quantum entanglement, one of the strangest of quantum mechanical phenomena, and certainly among the hardest to intuitively grasp, occurs when two particles interact in a way that makes their quantum states inseparable. After the interaction, the wave function describing both particles is not the product of two independent wave functions, but a single entangled wave function. Neither particle has definite properties independently. The two particles are described only together as a single quantum system, regardless of the physical distance between them. When you measure a property of one particle, the entangled partner's corresponding property is instantly determined, not because any signal traveled between them, but because the two particles' properties were correlated by their shared quantum history. This does not allow information to be transmitted faster than light. The measurement results are individually random. You cannot control what value you get when you measure your particle, so you cannot use it to send a message to your partner across the room or across the galaxy. But the correlations between results, revealed only when you compare measurements afterward, are stronger than any classical correlation could produce. They violate Bell's inequalities. They confirm that the particles were genuinely entangled, genuinely sharing a quantum state, in a way that has no classical analog. Your body contains trillions of atoms, and those atoms are constantly interacting with each other and with photons from their environment. At the scale of a whole body, quantum entanglement between different parts of your body is washed out almost instantly by the constant thermal bombardment of molecules and photons, a process called decoherence. But inside individual biological molecules, quantum coherence plays genuine functional roles. The photosynthesis machinery in plant cells uses quantum coherence to transfer energy between molecules with extraordinary efficiency, an efficiency that calculations show cannot be explained classically. The navigational sense of migratory birds appears to rely on quantum effects in a class of proteins in the eye that are sensitive to Earth's magnetic field. Your body is not a classical object pretending to be quantum. It is a quantum object operating at a scale where quantum effects mostly average out, but not entirely. Even DNA, the molecule encoding the blueprint for every living organism, is subject to quantum mechanical processes in ways that may be biologically relevant. The hydrogen bonds holding the two strands of the double helix together involve protons that can quantum tunnel from one strand to the other, occasionally producing rare tautomeric forms of DNA bases that have different hydrogen bonding properties and can lead to mutations when DNA is replicated. Evolution itself, the process by which life has diversified and complexified over billions of years, may have quantum mechanics at its roots, in the form of quantum mechanical errors in DNA replication that generate the variation on which natural selection acts. The diversity of life, every species that has ever existed, every adaptation, every innovation in the history of biology, may ultimately trace back to quantum tunneling events in the hydrogen bonds of DNA molecules. This is the world the atom opens onto, not a tidy, comprehensible world of little spheres clicking together in predictable ways, but a deep, strange, probabilistic world where matter and energy and information are entangled in ways that blur the boundaries between them. where the act of measurement is not passive observation, but active participation, where the properties of objects do not exist independently of the processes by which they are measured, where the line between observer and observed becomes, in certain experiments, disturbingly ambiguous. The atom is the doorway. Everything else, chemistry, biology, materials science, nuclear physics, quantum computing, the energy of stars, the diversity of life, the evolution of the cosmos, lives on the other side of that doorway. In the strange territory the atom opens up when you look inside it honestly and let the mathematics tell you what is there rather than what you expected to find. You are standing on that doorway now. You have been standing on it your entire life, every atom of your body pressing against the atoms of everything you have ever encountered, never quite touching, separated always by the irreducible gap of quantum emptiness and electromagnetic force. The doorway is not in front of you. It is not beneath you. It is you. It is the substance of your hands, the structure of your bones, the chemistry of your thoughts, and it opens onto a universe that is far larger, far stranger, and far more generous with its wonders than the solid, sensible world your senses construct for you each morning when you open your eyes. The sensory world is real. The quantum world underneath it is more real. And the relationship between them, the way unimaginable quantum strangeness averages and scales and organizes itself into the dependable, touchable, beautiful world of human experience, is perhaps the deepest mystery and the greatest achievement in all of nature. All of it. Every mountain, every ocean, every heartbeat, every thought. From almost nothing at all. That is what an atom is. That is what you are made of. That is what this is.